Here's an example on the randomized block design. Crescent Oil has developed 3 new blends of gasoline and must decide which blend or blends to produce and distribute. A study of the miles per gallon ratings of the 3 blends is being conducted to determine if the mean ratings are the same for the 3 blends. So basically they've got 3 different types of gasoline: blend X, blend Y, and blend Z, we're going to see in a moment. And they want to see if they give you the same average miles per gallon or if they're not the same. So firstly, we're going to look at the factor. The factor is the thing that brings about change, the generic factor that brings about change. And that factor is the gasoline blend. If I have 3 different blends, that means there are 3 different treatments or 3 different levels. So the factor is just gasoline, and the treatments are the 3 blends that we're going to have. They're also known as 3 different levels. The response variable, what are we going to record? Well, if we're interested in the miles per gallon to see if the gasoline gives you the same miles per gallon, that's what we're going to be recording, the miles per gallon. So our response variables would be miles per gallon. There is one more thing that we talk about here, which is blocks. But I'm going to leave blocks out for the moment, and I'm going to actually show you the example. I think it'd be easier to explain blocks from there. So these are the actual results. It says that they looked at basically 5 different automobiles, 5 different vehicles, and they blocked them together. Let me try and explain what that means. If I had 3 different vehicles, not 5, let's just say 3, and one of them was a Bugatti Chiron. Now I know that for a Bugatti Chiron, average miles to the gallon is around 11. And I had another car which is a Honda Accord. And let's just say the average miles per gallon for that one is about 32. And then I have some sort of Prius, and the average miles per gallon for the Prius is, say, 54 miles to the gallon. Now, if I put the same gasoline in each of these 3 cars, exactly the same gasoline, I'm going to get different miles per gallon coming out from each of these cars. And it's not anything to do with the gasoline. I can use exactly the same gasoline. It's a function or result of the car, the engines on the cars. So can you imagine if I actually put blend X into the Chiron, blend Y into the Accord, and blend Z into the Prius? When I get my results, supposing the results come back that the different gasoline blends give me a different average miles per gallon, blend X, blend Y, and blend Z give me a different average miles per gallon. Is that because of the gasoline, or is it because of the cars? And the answer is, I don't know. There's a good chance that it's because of the cars, the different cars. So to eliminate that, to eliminate this noise coming in, to make everything more equal, what I'm going to do is I'm going to block them together. So say, for example, automobile 1 is the Chiron. And what I'm going to do is I'm going to take the Chiron and I'm going to put in turn blend X, run it, see how many miles to the gallon I get, clean out the tank, then put blend X in it, see how many miles per gallon I get, clean out the tank, and then put blend Z in it. Another way of doing it is to take 3 identical Chirons and put blend X in one, blend Y in the other, and blend Z in the other. But at any rate, they're all Bugatti Chirons, and when I block them off like this, any differences in the mileage or any results I get are not based on comparing a different car. I'm not comparing a Chiron to an Accord. I'm comparing the same Chiron, and the only difference is the blend of gasoline. So I've isolated a blend of gasoline, and that's the only thing that can make a difference to my results. And then likewise, I can actually go down to automobile 2, and that could be the Accord, and then I can go to the Prius, and that could be automobile 3. So basically I can block them all together. This could be my Accord, and then I can block off the Prius. So any discrepancies, any differences I get are going to be due to the gasoline blend and nothing else. So that's the explanation. So if I just go backwards, it says that the blocks are the automobiles. I'm blocking by the different automobiles, by the Chiron, by the Prius, by the Honda Accord. And so I'm going to go off now and I'll actually do this question. We're going to do that question in Excel. In this particular question, there are 5 blocks. So we're going to go off to Excel, where I've already put this data. So to run this data, we consider there to be, or at least Excel considers there to be 2 factors. There's some discrepancy on which books you read, but Excel considers this to be 2 factors. One factor is the blend of gasoline that can bring about change, and the secondary factor is the different automobiles. We can actually also check that. We can check to see, does the Chiron give the same average miles per gallon as the Accord, gives the same average mileage as the Prius, and any other cars you've actually blocked in there. So this is a 2-factor ANOVA. So it's very quick to actually do. So we need to go to data up the top, and then data analysis over to the right. And so we need, it's not single factor anymore, and this is not 2-factor with replication, it's just 2-factor without replication. We didn't replicate any of our experiments. When I took, say for example, blend X, I put it into the Chiron just one time. I didn't try putting blend X into a Chiron a second time and get a result. I just did everything once, so there's no replication. So now I need to put my input data, and so note, when you put your input data for the block design, you actually have to include this first column, the actual block column as well. When we did single factor ANOVA, we didn't actually include this first column. And I did include labels, and let's take alpha to be 5%, and let's put the output range to be here. And that is how fast we should be going to our results. Output range, input range, just make sure. Oh, that moved for some reason. Just be very careful when you do this, because sometimes it will move on you. Okay, and they're the results. The actual averages for blend X, blend Y, and blend Z, they're actually given to us as well. So the averages for blend X, Y, and Z, they're right there. So but if you had this sample data, so the average miles per gallon for X, Y, and Z are 29.8, 28.8, and 28.4. Would you say that those averages are close enough to suggest that the gasolines work the same, and any errors we're getting, any discrepancies we're getting are due to sampling, because samples aren't exact? Or would you say there's a real difference between the gasoline blends? And you've also got the variance in the actual results. So let's move on. So these are the results down here. I'm just going to copy this down to here so I don't have to keep scrolling. Just paste it to here. So there you go. So it says rows, columns, and error. Well, what we're mainly interested in is if the average miles per gallon for the different blends are the same or not the same. So what we're actually interested in doing is we're interested in seeing if the, let's say this, if the average miles per gallon, oh sorry, I do that in a, if the average miles per gallon for blend 1 are equal to the average miles per gallon for blend 2, equal the average miles per gallon for blend 3. And that's going to be our null hypothesis. This is done exactly the same way as the single factor from this point. The alternative hypothesis is that they're not all the same. So not all the means are the same, so not all the same. And with all of these ANOVA problems, you're always going to get, if you use a critical value approach, you're going to get a one-tailed test with the rejection to the right-hand side, always. So all we need is the critical value in the test statistic to complete this test, and that's going to be the critical value right there. And this is going to be our do not reject over here in green. So do not reject H0. And then we're going to have the reject H0 over here. Reject H0. And alpha is going to be 5%. So the size of that rejection zone, if we measured it, it's going to be 5%. So using the critical value approach, which data do I take from in here? Well, the data that you're going to take from in here is going to be for the different blends of gasoline. Now the blends of gasoline are in the columns. So I need to use the column data. The column data is going to refer to the different blends of gasoline. So if I'm going to use the critical value approach, I need the critical value for the columns. So the critical value is 4.4, it's right there. It's 4.46. So it says 4.46, 4.46. And the test statistic is going to be 3.8. So 3.8 is going to be, I don't know, hit somewhere here. So our conclusion is do not reject H0. Oops, I think I'm too close to the bottom here. Let me just scroll a little bit. 3.8. And our conclusion is do not reject H0, so we go with H0. So this is saying that on average, the gasoline blends give us about the same amount of mileage. Now, even though the course doesn't say this, I'm going to show you a second result you can get, because we're obviously given something called the rows. Okay, so these are the rows. What would the rows give us? What do we have in the rows? Well, the rows are these guys over here. This is one row, this is another row, this is another row, and so on. We've got 5 rows. So you know what we're checking there? Let's see what we're checking for the rows. We're checking to see a null hypothesis of mu1 equals mu2 equals mu3 equals mu4 equals mu5. So we're checking to see if the average mileage of the different automobiles is the same. That's what we're checking right there, because when we're checking the actual rows, we have the different automobiles in the rows, and the alternative hypothesis is that they're not all the same. And again, it's going to lead to a one-tailed test with rejection to the right-hand side. So one-tailed test. Let's do that again. If you use the critical value approach again, have the do not reject to the left. Do not reject H0. Reject over here. Reject H0. Using the critical value approach, let's go for the critical value, which is 3.8. 3.87, 3.83, sorry, 3.8. And then the test statistic is 18. Oh wow, 18 is going to be way up here. That's the test statistic in here. 18. Conclusion now for this is actually you reject H0 and go with the alternative. So that's actually saying that the average mile per gallon for the different cars is not the same. not all the cars give you the same average miles per gallon, which is very interesting because we blocked it and we were able to see the effect of the gasoline and also separately the effect of the blocks. And if we'd have just run this as a single factor ANOVA instead of a two-factor ANOVA, we may have got a different results for the gasoline, because the different automobiles, we're told right here, they don't all act the same way. They act in a different way. Some, at least one does, they're not all the same. So because they don't act the same way, that could have influenced the result, but we've actually stripped that out. We've stripped out the effect of the automobile and we've just looked at the effect of the gasoline. So that's the whole point of blocking. And we could have actually used the p-value approach as well. So if we want to use the p-value approach, remember, if alpha is greater than the p-value, that means you reject H0. And if alpha is smaller than the p-value, you do not reject H0. And for the first case, well, alpha was 5%. And for the first case, which was the columns, the p-value is 6.9%. So obviously the p-value here is greater than alpha, which means do not reject again, so that implies do not reject. And if we do the same result, we'll do the same test over here, sorry. So alpha is 5% for this question. If you're not given alpha, assume it's 5%. And the p-value for the second part of the question, where we're looking at the rows, the p-value is approximately 0. Can you see it in there? It's approximately 0. So let's put p approximately equal to 0. So in this case, alpha is greater than or equal to the p-value. 5% is greater than or equal to 0. So that means that reject H0. That's the same result we got up here. See, reject H0.